In this video, we are presenting our paper with the title is Using the MagPilot Library to Analyze the Ferrofluid in the Magnetic Field Sourcing from Cylinder. The author is Yoyo Adistyo Laksono, Nugroho Adi Pramono, Sunaryono, Ahmad Taufik. We are from Department of Physics, Universitas Negeri Malang. Background to the problem: the application of magnetic nanoparticle, or MNP, is in the biological and biomedical fields. From the first reference, the behavior of NMP in a fluid affected by an external magnetic field is influenced by the magnetic property of the carrier and the performance of the magnetic system, the interaction of magnetic force and Stokes resistance, and the diffusion motion of the particle. From reference 3 and 4. To produce a strong magnetic field can be done in two ways, namely permanent magnet, 5 and 6 reference, or electromagnetic, 7 or 8 reference. One of the research is observing the movement of NNP under a magnetic field generated electromagnetically from two small hollow cylinder material. From 9 reference. The research was carried out by first performing numerical simulation using COMSOL and MATLAB software. The result of the research showed conformity with the experimental result by comparing the MNP from form of camera recording with numerical data. COMSOL Multiphysics and MATLAB is proprietary software. In this research, we try to write down using MagPilot library, which is free software. In version 4, there is new function cylinder segment from reference 12 to create permanent magnetic source. This function need to validate with experimental result. The theory between in MNP in fluid: if magnetic nanoparticle MNP is subject to external magnetic, there are 5 forces acting it. First, the magnetic force, the fluidic force, buoyancy, gravitational, and interaction between particles. According to reference 13, buoyancy, gravitational, and interaction between particles can be neglected. The magnetic force Fm from external magnetic field is shown in this equation, where mu0 is magnetic permeability in free space, Vm is the volume of the MNT, Phi is magnetic susceptibility, and Rm is the external magnetic field. The fluidic force Fs, this is aroused when NNP moving in fluid. This is Stokes equation, where τ is viscosity, Rp is hydrodynamic radius, Vp is the velocity of energy, and U is the velocity of fluid. For permanent magnetic source using this equation, where R denotes the position, V is the volume of magnetic body with a surface S, and N is a vector normal to the surface S. From reference 50. And the method: the diagram of experiment by pi in left, and the image result from cylinder segment function is in right. This is the picture from experiment, and this is from Python library MagPilot with function cylinder segment. This is a cylinder with hollow in the center. The numerical result, simulation result in P is normalized. So the Python program in MagPilot uses the get P function, and the result will be normalized. So the value of P between 0 to 1. The result of the numerical simulation are graphed using the stream plot and counter F function from the matplotlib library. The stream plot function generates magnetic line, while counter F is used to identify the B field strength. The result was then compared to the picture from Wei and Wang. The result is shown in the right. This is a cylinder and this is a hollow in the center of cylinder. This is a magnetic ferro MNT, NMPN fluid, ferromagnetic particle. We inserted in the red rectangle area. Comparison picture by picture and maximum and minimum normalization. This is from COMSOL and this is from McPilip. The max value is 0.555 and in the from McPilip the max is 0.55. The minimum value is 0.0678 and this minimum from McPilip is minus 0.12. The picture-to-picture comparison show the same poster. Not we shall try to make same color legend for final paper. The numerical result data show that the maximum value of B is the same, which is 0.55, while the minimum result is not the same, and the relative error is 45%. This happened because the module in COMSOL used the finite element method, FEM, while McPilip used an analytical approach. According to the reference, the source of error from finite element method are discretization errors, round-off errors, and solution errors. So this is a different from analytical and finite element method. This finite element method is approaching using numerical, and this is some error. So there is a difference. Conclusion: in this research, McPilip has been used to analyze the magnetic field from two cylinders with a hole in the middle. The results show conformity with the result of numerical simulation using another paid software. So, McPilip is suitable for studying fields related to magnetism. The differences that occur are unavoidable because the numerical methods are not the same as analytical method. The future work: create real-time simulation with animated NNT in fluid using various magnetic sources. Acknowledgement: this research is funded by PNBP Universitas Negeri Malang. The author acknowledged LP2M for all the support during this research. This is a difference. Thank you for your attention. If you have any suggestion and question regarding this presentation, I would really appreciate it. Thank you.